please. All right. Good afternoon, everybody, or early evening. Can you guys hear me all right? Can someone just confirm on the chat that you guys can hear me okay? There's a bit of a delay on my end, so if you ask a question, it might take me a minute to get to it. But if someone can just confirm that we're okay, I think the audio should be working. All right, loud and clear. Awesome. All right, Camille, what is your question about spanning sets? While you write a question up, Eugene, I will answer your question about number 7 on homework number 9. Okay. All right, so let's start here. So number 7 on homework 9, we're asked to calculate the norm of A. All right, given the above inner product, right? So that means that what we define here to be the trace okay, so we'll use that inner product from above. Okay, so now from here, again, norm of A is use that notation. So we would like to calculate that, all right? And again, the trace is just, we do this multiplication and then we just add up the diagonals, right? So in terms of the trace of A transpose A. Okay, so now I'm gonna get into this part here. Let's write, I'm gonna focus on this and I'll come back to this whole operation in a second, right? A transpose A is equal to -1, 7. 6, 2 times negative 1, 7, 6, 2. Okay, and multiplying that out, we'll get 1 plus 36. We get 37 here, and then here we'll get negative 7 plus 12. We get 5. All right, and then here we get negative 7 plus 12. We get 5, and here 49 plus 4. We get 53. Okay, so I just did this matrix multiplication, right? So now again, we go back to here, what we have written here. We're looking for the trace of this matrix. And again, the trace, as we saw from above, is the sum of the entries of the main diagonal. So that'll be, what is that, 10, 8, 90. Okay, so or 3 root 10. So we define the norm of A to be 3 root 10. Okay, so that's it, right? Once we've identified the norm, again, right? Norm is not always in R to the n, right? It's whatever space that we're dealing with. In this case, we're in the matrix space, and they define the norm to be the trace. No, not the spans, right? So here, all right, so number 11 on homework 9, all right. All right, I got that written down, Jennifer. Okay, so a basis is, by definition, it's two things, right? It is a, well, basis starts off with a set S with however many vectors, right? We'll just say n vectors. Okay, so the span of S is the linear combination of all of these vectors in the set. All right. So this is the span of S, and this is the set S. Right? When we refer to a basis, we are referring to the set here. We say the set S is, in order, if it's a basis, then S has to be Li, and it also has to span, in this case, span S. All right. If we say that, if we know that the span of S is equal to V, then we could say S is a basis for V. All right, so we're not saying that all the linear combinations are linearly independent, only this set C, this set S. Only that set S, all right? Does that make sense, Camille? Okay, all right, so now let's take a look at number 11, homework 9. Okay, so let's jump here. Homework 9, number 11. Okay, so we want to find a into an orthonormal. Okay, so we're going to use Gram-Schmidt, but again, remember this is only orthogonal. Okay, so once we find that, we have to divide by the magnitude in order to normalize it. Okay, all right. Okay. Alrighty then. So let's take a look at here. We have our inner product. Okay, and we have our ordered set. 1x squared. All right, let me recall the formula here. Okay, so we'll let this be our W1, W2, and W3. All right. Okay. Okay, so let's see here. Let me, hold on. I need to look up the damn formula for the Gram-Schmidt. Okay, so the first one is easy enough, right? We're going to let V1 equal to W. All right. Okay. Okay, so let's say, well, let me see here. Well, they should just be polynomials, right? I think we're just doing the norm of that between -1 to 1. We're just going to get some kind of root, right? Some constant. Is there something that is that I'm missing here, Jennifer? Because if we look at this, then if we're just dividing by the norm of our W sub 1, then the first one is 1. So we just have 1 squared. I mean, this one isn't too bad, right, in the norm square root. So here we get 1x is root 2. Right, and hold on, this one I think I have off the top here. Okay, so I think, let me look up the answer here, because I think I have that one off the top here. Okay. All right, let's just do the next one. I'll do one more, and then I'll normalize the other one just to see if we're on the right track. Okay, so then the next one, we get V2. Okay, so plus 1 over x. 1 over x? Huh. Okay, so let's take a look. Well, let's look at this one, x minus 1. If we look at that one is our, and how do we turn that into a normal vector? Yeah, I don't think there should be an x here. All right, let me just work this out so we could all be on the right page here. Okay, so okay, so equals to 1. V2 is going to be W2 minus, in this case, here, W1 with the inner product of V1. Excuse me, that's V2. Okay. Okay, so let's take a look at this, right? Where again here our W2 is the polynomial x. Okay, so in this case here, let's take a look at here V1 squared. V1. Okay, so that's x. So we get 2. Okay, and then here the inner product between W1 and V1. All right, and that gives us -1, 2, 2. Okay. All right, so putting all that together, W2, we get x minus, here we just get 1 and then 1. Okay. All right. Okay. Okay, so then, see, did I miss something, Hasbro? Ah, I see. This should be W2. Excuse me. Ah, okay. All right. So then x, and then here that should be from -1. That one's fine. Yeah. That should be 0. All right. That's what you're talking about, right? Sorry about that. Okay, so that means that V2 should be just X. Okay. All right, so now we have, so far, 1X. All right, and now let's look at V3. All right, V3. In this case, we'll get from -1 to 1, we'll get W3, which is X squared. And then minus, here we'll get W3. And again, here W3 is X squared. W3 V1, the norm of V1 squared times V1 minus W3 V2 . Right, all over the norm of V2 squared and times V2. Okay. All right. So here, let's see. I know this already. That one is 2. So let's take a look at these inner products here. W3, V1 of W3 is X squared. Okay, and here we get 1/3 X cubed from 1 to -1. So it's 2/3. Ah. Yes, they should all be W3. Okay. All right. Okay then, so here we have that for W3 V1, the inner product of those, and then W3 V2. And W3 we said was X squared. That is correct, Eugene. Okay, so from here, W3, we get X2, and then V2 is X, so we get X cubed, and yep, so that would be 0. Okay, so now what do we have here? So that one goes away, and then we're left with this thing here. All right. Okay. So we get that for V3. Okay, and I think that's what a couple of you had gotten that as well, right? All right, let me just look back here. Okay, so we got at least two of you confirming that this is what we got. So we got for our orthogonal bases to be this, right? So now we know this basis is orthogonal. And to normalize it, we'll do that, and that should give me √2. Okay, and then the other one, the norm of x, we get of x squared. Okay, and then this gives me +1/2. Okay, root 2 over 3. All right, and then the last one, the norm of x squared minus 1/3. So we'll do this integral, and again, just be careful here. Let me do this. All right, I won't finish that up. I'm assuming we can get it from there. But once you get that, then you'll get the coefficients that go in each one of those, in front of each one of those polynomials. All right. I think maybe Jennifer, you made I think a mistake along the way, but the normalizing shouldn't be too bad. They're just being taking integrals, and we're dealing with polynomials, so that should be okay. All right. Okay, so let's see. Next, I wrote a couple of these down here. We got number 11 on homework 9. All right, so I'm just going to jump into the next one, right? Because we got a limited amount of time and a lot of questions. So let's see here. 11, number 11. Excuse me. Well, that wasn't it. Let's see. The next one on deck was number 6. All right. Okay, so this is they tell me that we're in the matrix space. Yeah, we did just do number 11. We're gonna do number 6. Okay, and then we said here, trace. All right, and we were asked to show this is a valid inner product. All right, I'm not gonna go through like every single step, but I am gonna set you up so that it looks a little less confusing than this here. All right. Why don't we do this? Let's say that B is some matrix that we'll call it that. Okay. And then A, we'll do the same thing. A11, A12, A21, A22. All right, where these are just any real numbers. All right, so I want to take that matrix and I want to put it into this product here, right? If I do the transpose, so let's take a look at this. B transpose of A would be B11, B12. Then it would look something like this. All right, and now let's take a look at what the product of this matrix would be. We'd get B11 times A11, right, and then here plus B21 times A21. Okay, and then here we get B11 A12 plus B21 A22. Right, again, I'm just doing the symbolic matrix multiplication, right, from here to here, and then from here to here. And then down here we'll get B12 okay, and then here we'll have B12 A12 times A22 B22. All right. And now if we look at the trace of this matrix, the trace of this matrix is the sum of those numbers, right? So the trace of B transpose A would be this sum. Okay, so when we do this, all right, so when we do that, what we're gonna do is we're gonna, instead of using the above notation, missing something here, B2, A12. All right, so instead of using the above trace notation, why don't we work with this? All right, and now show that this is a valid inner product. All right, and now that becomes with one of the ones that I did in class where we had a function from R2 and we define a different inner product in there. Just think of it that way, right? Where in this case, these are the elements that you use and show those properties that the inner product has to hold, that it's symmetric, and so forth. Okay, I don't know who asked this, but I think this should get you on your way, right? Now when it's like this is just plugging in numbers and showing that one form is equal to the other form. Is that correct? Is that clear up to this point here? Okay. All right. Okay, so now the next one. This is a function of the elements of the matrix, right? So in this case, not just A and B, right? A are these elements in the matrix, right? So A11 is the first element of the matrix. B11 is our first element in the matrix. So when you have a matrix like this, they come from, these are the A's and B's, right? They're elements in our matrix A and our matrix B. And then we just wrote them as a product of real numbers, a product and sum. Yeah, you can think of it as a function of A's, elements of A and element of matrix B. Okay, does that make sense, Orai? Okay. Can we do 3B? Let's see. Okay. So let's see here. So let's tackle that one. Homework number 9, number 3. Well, I need to do 3A in order to get to 3B, but that shouldn't be a problem here. Let's see here. Okay, so when we're working with this, so in this problem number 3, we want my linearly independent subset that forms a basis for the space spanned by these vectors here. All right, so in this case, I'm going to change when I want my subset should come from the given set. All right, 2A. I'll put that on the list, Gursarat. Okay, so we have this, we need a subset here, a linearly independent subset. So when we need the subset to come from this set of vectors, what I'm going to do is I'm going to make those vectors to be, right, my column vectors, right? So here V1, we get 1, 0, 1, 1. Here we'll have -3, 3, 7, 1, -1, 3, 9, 3, and V4, -5, 3, 5, -1. Okay, and I'm going to do some operations to here. All right. Okay, give me a second here. I need to. Okay, so give me a second while I'm gonna do this matrix math here. I'm not gonna do this in my head or write it out. I'm gonna use some technology, but give me a minute to just compute it. Okay. Okay, so if I do this here, row operations, I do get should get something like this. All right. All right, which means, which means that here we'll choose the ones with the leading ones, V1 and V2. Right, those would be our, excuse me. All right. All right. Okay, which means that we have now this V1, V2 to be written like this. Or that is my linearly independent subset. Okay, so that means that we would like to write, and then from here, V3. Okay. All right, and then from here, we'd like to find those C1, C2, right? Again, I think at this point, once we get this in this manner, you can identify the linearly independent subset. I think you guys can do this from here, right? Simply setting up a system of equations there that you have to solve for C1 and C2. Okay? All right. Are we okay finishing it out from here? Okay. All right. Then from there, let's see. Oh yeah, well, we're not done yet, right? That is correct, Jennifer. The last two rows are also that, but then again, right? You can still have a pivot in one, and then it's negative R2 times the other twos to get you the rows of zeros. Then I pick V3, V1. Well, if you have this, Is this what you're referring to, Jennifer? Something like this? Okay, well, remember, right, in our system of equations, right, if we're going to work through this, then we would like to, this is our pivot. Once we have all zeros here, we choose this to be our next pivot, and we get all zeros under here. So this is not done yet. We want to get this in reduced echelon form. Okay? So the process works in getting it in reduced echelon form, which means that once we're here, we're not done yet, right? We take negative R2, add it to R3, add it to R4, and those are my new R4s. And then that should get you to up here when we get all zeros there. Okay, so once we're here, we're not done yet, right? We still have some work to do to get it to reduced echelon form. Okay, switch row 2 and 3. Switch row 2. Yeah, well, you could switch row 2 and row 3, but again, the columns, I mean, in the end, you should still get this, though, right? And again, all right, so you can switch rows 2s and 3s, but again, what we're focusing on here, the columns represent our V1, V2. That shouldn't change this part. This part should be the same. Okay, yeah, you could switch the rows. That's okay. That's why we wrote them as column vectors, to keep track of them easily. Okay, so let's see here. All right, I got a couple of them on my list here before. No. You choose Gursarat. You choose V1 to be the regular column vector, right? You go back to the original V1 and the original V2 because they want the vectors to come from this set. It had to come from V1 and V2. Okay, Gursarat? All right, let's see here. Next on my list, I have number 12 and number 13 here. Okay. Okay, so let's look at number 12. And again, I think I left off for 12A. At the end, it should say relative to basis S. All right, so it should say that. All right, sorry I didn't write that on there. Okay, so it should say that relative to basis S, which means that for part A, what we'd like to do is, again, right, it comes to solving out two, negative 1, 3. All right, so again, right here, at this point, you just set up a system of equations, and you solve this system of equations. Okay, and I think you can take that one from there. I think Lindsay, you asked that, right? Gyongjin. And for the second part, what you would do is, if you're given so the second part, they give you the coordinate vector. So here, WS is equal to 6, negative 1, 4. All right, and again, right, given this, then to find W, remember the notation here, right? I think here what's causing us problems is probably the notation. This notation is just the coordinate vector relative to the basis S. If you want to find W, you take 6 times V1 minus V2 plus 4 V3. All right, and then there's no solving an equation here. From there, we just plug in numbers, multiply it out, and then we'll get the vector W. All right, part B is the easy part. All right, we just plug in and multiply. Okay? Yeah, remember, right? I think it's just a notation, right? This is telling me this is the coordinate vector. So that's where those numbers go. All right. Okay, so here, let's see here. So someone asked about 2A. All right, I'll get 13 after this. I think someone asked 2A, and then I'll do 13. And then someone asked on number 5 on the sample exam. And then number 8 on homework 9. Okay, so I'll work through those as quickly as I can, okay? All right. Okay, so I would like to show this. All right, so here we're in a real inner product space. So all that means is that the inner product is defined, which means that this is true by definition. Excuse me. All right, so that's the definition of an inner product. So this is true. So I would like to show that one of these is equal to 0. Okay, so true by definition. So my next step would be to show that one of these is equal to the number 0. Okay, so let's do this. Why don't we let why don't we do something like this, right? Where W is any vector in my vector space. And 0 is the scalar 0. Okay, this is true. Again, now this goes back to just properties of our vector space. Right, this was one of the axioms. This has to be true. Okay, so now we have this. So let's rewrite this in this form here, right? And again, why do I want to do that? Well, if this is a scalar, the definition of an inner product allows me to do this. All right? But now once I'm outside here, this is a real number, and this is the real number 0. So 0 times any real number is equal to 0. And that should wrap up our proof. Okay? All right. We're okay on that one. On 2B. Or excuse me, 2A. All right. No, V is not the 0 vector. V is any vector, right? That was that was what they. We're not assuming V is the 0 vector. V can be any vector. Okay. Okay. All right. So we're good from here. Let's look at someone 13. C and D. All right. Give me a second here. Okay, so Gyunjin, you did A and B then, so you found the transition matrix. Okay, so once you do that, if you want to compute the coordinate matrix, then you would just W is equal to 3 negative 5. Ah, okay, I see. Okay, so what you would do then, I don't have this off the bat here, but all you would do here is, all right, if you want to find this thing right here, WB prime, then what you would do is you take here, in this case, you take 3 negative 5. All right, or W. Okay, all right. So B prime is V1, V2. So to compute this, the coordinate matrix with respect to V prime, what we would do is we take this 3 negative 5, and we set it equal to C1 from B. You would use it from B, because now you would look at the transition matrix from B to B prime. Hold on a second. Let's see here. You use it from B. It would be from B, right? If we're looking for WB prime here, we would use the transition matrix from B to B prime. Okay. So this would come from, it would come from part B. Okay, so yeah, it will come from part B, because then you would have, if you're using the transition from B to B prime, you would have yes, you can also do that, Odai. Correct, yeah. Yeah, that would be correct, Lindsay. And Odai, you could do it. This is only one way to do this. You can do this the other way, where we just did the the linear equations. That would be okay too. Okay? So I think here is just an exercise to see that there's more than one way to find to solve this problem. Once we found the transition matrix, right? Again, if they're asking us to find the transition matrix, then let's just use it to solve the problem as a matrix multiplication instead of solving linear equations. But both ways would work. Okay, does that make sense? Would I? Okay, let's, I want to get through someone has something on the sample review, the sample exam on number 5. All right. Whoa. What are you confused in, Lindsay? Oh, okay, I think Orai was just saying that we don't have to do the matrix multiplication, which he was correct. But again, right, once we have the transition matrix, then we're just going to do it through the matrix multiplication, which is what you were trying to do and trying to figure out which matrix to use. I think what Odai had mentioned is that we can just look for, if our concern is to find this, right, if we just want to find the coordinate vectors in terms of our basis B, B is just a standard basis, right? We could just say 1, 0, 0, 1. Right, then we could say, all right, if W is the vector 3, -5. Then we can just say we could just do it this way, right? Where we just set up a system of equations, right? When this one should be right away, C1 is 3, C2 is -5. Okay, I think that's all that Odai was mentioning, it that we could do this another way, and true, we can do it another way. I think here is just an exercise in looking at in generating that transition matrix P. Okay. All right. Can we move on to another? Oh, okay. All right. Let's move on to another problem here. Hold on. Let me get some more white paper. Okay, so in the review number 5, it says we have the Euclidean inner product. And all this means is that it's the natural dot product that we're used to seeing. So if we're in R3, then this would just be U1 V1 plus U2 V2 plus U3 V3. Right? And R to the n, right? So again, we're not limited to be to R3, but just as an example here, that that's what I mean by the Euclidean inner product. Okay, all right. Okay, so from here, let's see. All right, so we would like to show, yeah. Okay, where you and then A is just Just the n by n matrix. Right. Okay, so if we think of the Euclidean inner product, then we think of it, again, we define that as just our dot product, right? U dot V. Okay, so why don't we do this? Let's think of this here. Okay, so if we think of here, all right, so if we think of our inner product, we think of that as U1, again, U1 V1 plus U2 V2 all the way to UN to V7. Okay, but what I would like to do, since I do have a matrix here in play, I would like to look at the inner product, or the dot product here, the Euclidean inner product, as let's look at it as a matrix multiplication. Okay, so if I'm given U dot V, I'll think of U here as a column matrix, right, where we'll have U1 through UN, and I'll think of V as another column matrix, V1 through Vn. Okay, so again, these are n by 1 and then n by 1. All right, so if I think of my dot product, or the Euclidean inner product, in this manner, here what I can say is, I said, all right, well, let me take a look at this product here, the V transpose times the vector, or the matrix U, I guess, here, if we're looking at matrices here. So V transpose would be V1 all the way to Vn, and then here we have U1 all the way to UN, right? So this is a 1 by n, and that's a n by 1. Okay, so the inner ones match up, and we're left with a 1 by 1, or a real number, right? So at least we get a real number here, and if we do the multiplication, U2 all the way up to V sub n, U sub n. All right. Excuse me. All right. Or in other words, we can think of this as U1 V1 over U sub n V sub n. Okay. Now, what does that mean? That means that I can think of V transpose. Yes, we can do them with rows. Just be careful how you treat. Just be careful that those products match up. All right, again, there's not much difference between a row and a row matrix or a column matrix. What we want to make sure is that we do the proper operations here, right? Now, the reason I chose to do them as column vectors is because now I have a definition here where V transpose times U is equals to U dot V, or in other words, this product here, or the inner product there. All right, well, now let's apply it to what we're trying to prove. All right, so we want to show here all right, now if I use this notation here, what we have here, we said that, all right, that would be U dotted with AB, all right, or U times AV, excuse me. All right, and that comes from the above here, right? Kind of working our way this way, right? And you see that's why I changed it from columns, I thought of them as column matrices instead of the row ones. But you can make it work. Again, just make sure all of the matrix operations work out okay. Okay, because then from here, right? Remember this is okay, so now here, applying some transpose properties, we get V transpose A transpose U. Because I defined it as a column. And in order for it to work out, the way I did this, again, this is how I defined it, right? Again, if you want to work through it as row matrices, then you're going to have to make sure that all of this, the proper representation of the dot product in terms of a matrix, right? So I thought of them as column, right? I defined this, right? Now you ask why I defined it in this way. Well, I want to take a look at this particular product here, V transpose times U. All right, here the inner matches up, so this is proper matrix multiplication, and as a result, we'll get a 1 by 1 or a real number. And the product here is this product here, right? Or in other words, the inner product, the Euclidean inner product, right? So all these three I've defined to be the same. Okay. So again, right, this is something that I define because I want to write the inner product as a product of matrices. If you don't do it this way, then you have to watch out where the transpose goes. But you do need a transpose in order to get a product of two matrices where you get a real number. Okay, so now I have a way to define a matrix here, or excuse me, the Euclidean inner product using matrix multiplication. Okay, so once I have this here, then I can apply that same logic up here, right here, right, where it's U dotted with this AV, but I can think of it as the multiplication of the transpose of this product here, AV times U. Again, now we're matrix multiplication here. And then matrix properties here. Okay, and now what we can do here is we could say, all right, what if I define this okay, and again, I just did a association here, and this is 1 by n. This one here is n by n. This is n by 1. Okay, so just to verify that all these work out okay. So here, this is okay, so I get an n by 1. And then here I get, these are the same, so I get a 1 by 1 or a real number, so it works out great. And again, using my definition here, when I have matrix multiplication here of the transpose and this, that's the same as the dot product of this with V trans, or V, excuse me, or in other words, A transpose vector U inner product with vector V. Right, and that gets us where we want to be. Okay. Any questions, anything that I can go back to on this one? Okay, so I have one more question here. Someone wanted me to do number 8 in homework 9. And I think, okay. All right. Okay, so homework number 9, number 8 here, and I believe you wanted 8B, right? Someone asked for 8B. Okay, so here we're looking for so if and only if okay. Okay, so here so we get this, right? And again, our assumption is that V is an inner product space. Okay, so if it's an inner product space, then I know here this is true if and only if x is equal to the 0 vector, right? Those are properties of the inner product. Okay, so here, if we go in this direction here, where we know that here the inner product is equal to 0, then we get the norm of x is equal to 0 Okay, so that part works out okay. If x is equal to the 0 vector, then we get the inner product of the zero vector, which is the numbers there. Okay, now the other part show that it's always positive, otherwise okay, so from here, if we take a look at, again, back to the definition here of our inner product. Okay. All right, so from here we could say, all right, definition or properties of inner product. This has to be true, and again, if working with this inequality, if we take the square root of both sides here, zero, or in other words, the norm of x is positive, or always greater than, oh, excuse me. We're assuming it's not the zero vector. All right. Okay. All right. Okay. We okay on this one, number 8 and homework 9, and then number 4. The last one. What do you mean by the last one? That it's always positive or 0 if it's the zero vector? Yes, no. What do you mean by the last one? Any other questions I can answer? Okay. I think if there's no more questions, I think we're going to call it a day here for today. All right. I'll be on campus tomorrow as well as Tuesday morning. If not, I'll see you guys on Tuesday. Okay. Thank you very much. I hope that this was helpful.